For the error detection and recovery, there's one basic mechanism that always exists, is the timeout. Or like the timeout have to exist because this is the very basic rudimentary way of recovering from some fatal problems. However, timeout is timeout. It's not that fast mechanism. And there's additional mechanism that was implemented as part of TCP. It's called the fast retransmit, or it's more usually referred as a 3 duplicate acknowledgements. And what it means that it's just some inference of that something bad happened, but it's not as bad as the kind of no packets are flowing and you have to retransmit after like really long time. Because those duplicate acknowledgement, especially 3 of them, can arrive relatively fast, especially if you're sending like hundreds of packets in flight without being acknowledged. And if most of them were delivered, then you will detect some additional problem happened. And what happens when the error detected is really up to specific TCP implementation. It can be as simple as starting from scratch, starting from sending very similar to go back N approach, or it can actually differentiate between timeout action and the kind of this 3 duplicate acknowledgement action. Because technically these are different problems in the network. In one case, there's a kind of when a timeout, it means that you haven't received a single acknowledgement for a long period of time. And in the second case, it means that you still receive an acknowledgement, but you just lost one of the packets that you transmitted in previous RTT were lost. So you may need to infer which packet was actually lost and retransmit it. So I'll talk about more about the windows and how TCP manages windows in the next lecture as part of the congestion control, because it's much more complicated topic. And today, for the last part of this, I will try to focus on the retransmission timeout. And what's important about retransmission timeout is that this timeout, it really depends on RTT, and RTT is kind of changes depending on where you are, where you're connected, and kind of what kind of buffering exists in the network. And it's the timeout itself should be not too small, because if you have a too small timeout, you have a spurious retransmissions, which will cause some additional problems in the network. But at the same time, you don't want to make it too large, because then you have very slow reaction to the bad behavior in the network. So what people are doing, what TCP is actually doing, is trying to set the retransmission timeout based on estimated value of RTT. And there's not just RTT, but rather RTT plus the estimated deviation or estimated jitter of the RTT. And I gave you a lot of formulas on this slide, but just to kind of remember, I mean, you probably need to remember these formulas as well, but they're quite simple. The whole logic behind these formulas is that every single time you can take a measurement of RTT, you're taking a measurement of RTT, and then you're trying to get the average among all the values that you collected or that you had. This is not real average, so this one is called a smooth average, or sometimes it's exponentially weighted smooth average, as ESWA. And what it means that it's whatever the value you had, it's kind of weighted against the value you're receiving. And eventually, if you're receiving the same value over and over again, the SRTT will be approaching that value. It may or may not reach it, but it will be approaching that value. It's just a simple way of doing per sample estimation of some kind of average value. Something similar is done using the deviation of RTT. It's just done on not with a sample, but rather with the difference between RTT. And the deviation RTT in this case is a measurement, like the average RTT versus the sample of RTT, and just averaging using different constant. And the constant that I gave you here was for alpha is 1/8, and beta is just 1/4. So this is a very common constant that have been used as part of the TCP stack on all operating systems. They can be adjusted, but usually these are the values people are using most of the time. There are a few more things that important on this slide is when one of them is initial RTO. Because initially, you have to have some kind of a value until you set the kind of have a meaningful measurement of RTT. You have nothing to deal with. So, but you still have to have some form of a timeout, at least when you send the SYN packet and you didn't hear from the SYN packet for a long time, you still have to kind of retransmit the SYN packet at some point of time. And this RTO usually is 3 seconds. Again, it can be adjusted, but this is usually the amount of time you can wait. And effectively, it means the granularity of the timeout, if you're not using any additional mechanisms, is this 3 seconds. 2 more exceptions in this rule. For the first, so initially you set this RTO for the 3 seconds. This is kind of the default value, like just waiting for any useful RTT measurement to arrive. As soon as you got the first measurement, then you adjust everything. So then you set the SRTT to the value, where is it? To the measured RTT. That's what you do as a first action. You set the deviation of RTT to half of it, and then you update RTO to be this SRTT, like sample, plus the 4 of deviation of RTTs. So effectively, you set it to 3 RTTs. So 1 of RTT that from the actual sample, and 4 halves of RTT of the sample, meaning like totally 3 RTTs. So this is very coarse, very coarse granular timeout that you're setting, but this is at least after initial RTT measurement. As whenever you keep receiving more measurements from the network, more samples of RTTs, then you will be adjusting RTT deviation, and potentially your RTO will be closer and closer to the actual smooth version of RTT. It still be a little bit larger because there's still some variation, but it will be approaching that value. I was a little bit careful saying first useful measurement of RTT because it's not just a measurement of RTT. And the reason I'm saying that it's not, sometimes there is actually ambiguity of what you're receiving, depending on whether you did retransmission or you did not do the retransmission. So for example, in this case, you send out something, then you time out, you send something again, and then you get acknowledgement. Now the question is, what did you get acknowledgement for? Did you get acknowledgement for the first packet, or you happen to time out too early and you got acknowledgement for the, whether you got the acknowledgement for the second packet that you transmitted, or it's simply that you time out too early and the acknowledgement just didn't reach you in time and you actually got the acknowledgement for the first packet that you sent out. So the options here are effectively multiple. You can assume that it was delay from the first retransmission, you can assume that it was delay from the second retransmission, or you can simply don't do the measurement. So the first 2 options are actually not that great, because in one case they will overestimate, in the other case it will underestimate the RTT sample, which will screw up the RTO calculations. And the last case, actually not that bad. And this is what we actually use as part of the so-called Karnes algorithm that we do on within the TCP, and which simply means if you don't know, like, without doubt what exactly this RTT is for, you just ignore it. Like, you have tons of other acknowledgement that will arrive in some point, and there's absolutely no point to just trying to squeeze all these RTT samples from every single RTT. So that's all about this Karnes algorithm. Beyond the Karnes algorithm is the timeout option that I quickly mentioned before. So if you use the, not timeout, but the timestamp option of TCP, if that one is used, then there's actually no ambiguity, because you no longer tying the time of sending packet toward the sequence number and the acknowledgement number, but rather you explicitly specify the time you send out specific packet, and then you measure time when the acknowledgement received for the specific packet. In this case, there is no ambiguity and you can calculate, but again, if we don't have that ability, don't use that option, we have to rely on Karnes algorithm to simply ignore ambiguous samples. And this is an additional example. I will not stop during the lecture, but I'll advise you to go over it, and I will try to ask additional questions with slightly different parameters so you can do some small exercise at home. To highlight the kind of estimation versus variation of RTT, so this one I got from one of the websites that publishes various measurements. So this is just saying that RTT is not really stable on the internet. So this one, RTT is at 250 milliseconds, means it was probably from Europe to United States, and the RTT actually varies quite a bit. And it can vary based on various parameters because there's a burstiness of traffic, and because of the burstiness of traffic, the buffers in the network routers will fill out and will reduce. And as soon as they fill out, your RTT measurement will go up. If you the buffering is reducing, the buffering goes down. So everything is constantly fluctuates. So, and you have some kind of understanding of RTT at any given point of time. There's an understanding of this smooth RTT, meaning like you smooth this a little bit. Plus, you can estimate the deviation of RTT and set the retransmission timeout using the RTT measurement, or like smooth RTT plus the deviation of RTT. So RTO is kind of usually very coarse granular way of detecting and recovering from problems. So there is this additional one, fast retransmit. And what is happening, you assume there is something bad happened if you received 3 duplicate acknowledgements, which means you received the acknowledgement for the new data and 3 duplicates the first one. So kind of whenever you look at some examples, you have to have 4 acknowledgements that's saying exactly the same sequence number. This would be 3 duplicates. So and as soon as it received those 3 duplicates acknowledgement, it simply assumes the packet that was the next packet indicated, or like the packet indicated, sorry, the byte indicates as part of this duplicate acknowledgement has been lost, or like some segment that include that byte. So the sender simply can retransmit like right away this packet and hopefully get the cumulative acknowledgement that acknowledges reasonably chunk of data. The exact action is actually dependent. In the simplest case, it can retransmit just one chunk, like the one packet that contained that segment that was a kind of repeated acknowledgement. In the more complicated cases, it can retransmit multiple, or like all of them, like similar to go backend, but usually it retransmit very small portions. And this is just a small illustration of exactly the same. Is kind of this, we send in 1, 2, 3, 4 packets. On the first packet, you send in the acknowledgement that you received that packet, and hopefully there was some other acknowledgement before for the smaller sequence numbers. Then the second packet got lost, and then the receiver received the 3rd, 4th, and 5th packet. And for each of them, it cannot yet say that it received all of them because it didn't receive them in sequence. So it's sending the duplicate acknowledgement, meaning it's just simply sending the cumulative acknowledgement saying, oh, this is, I received in order of 595. I received something, but in order I received 595. I received something, but in order I received 592. And with this signal, effectively this receiver can detect that something bad happened and retransmit the 592 byte and maybe additional bytes that they're available bytes to send out. Again, how much, it really depends on the sender, but in this case it transmits that those 100 bytes, and everything will continue normal, and the transmission will recover quite quickly from this problem.